All right, welcome back. Unfortunately, I did not record my own audio last time, although I got all of yours, and I didn't want to post a YouTube video where it was just answers to questions you couldn't hear being asked. So I have Vivian here with me to help make sure that I don't make any silly mistakes as I go through, um, as we try to get through all of the stuff that we did in class as fast as possible for physics. Um, I'm going to leave the annotations that we came up with together in class. So you'll see all the notes that we wrote last time, and I'll just write on top of those. So this is the 2017 free response questions for mechanical physics, question 2. Um, okay, so I have an inclined plane here, laser point. I've got an inclined plane here with a block of some mass that we're going to drop down the inclined plane and then run into this spring. So we're starting at rest from the top of the inclined plane. We're going to travel down the inclined plane and then make a smooth transition onto a horizontal surface. While we're on the horizontal surface, there is negligible friction between the block and the plane. And once we hit the spring has negligible mass. I want to express all answers for parts A, B, and C in terms of the mass of the block, the height of the inclined plane, the spring constant K, and any other physical constants, such as gravity, as appropriate. So for the first part, I want to derive an expression for the speed of the block just before it collides with the spring, the instant before we hit the spring. So to find the velocity, I can take our potential energy and set it equal to our kinetic energy. So our potential energy due to gravity would be mgh. Um, and then our kinetic energy at the end of the inclined plane, once all of our potential has been converted to kinetic energy, should be 1/2 of mv squared. So I can use this equation to solve for our velocity. So I would multiply both sides by 2, divide both sides by m, which will make our m's cancel. So that gives me 2gh, and then take the square root of both sides. Gives me our velocity is equal to the square root of 2gh. Because friction is negligible, there is no horizontal forces of acceleration that would change our velocity. So that means our velocity is going to be constant if there's no friction from the bottom of this inclined plane until the instant we hit the spring. Any questions on the first part?
No question. You have all their presentation.
Okay, second part. We're asked, is the speed halfway down the incline, so the speed at this point, going to be greater than, equal to, or less than half the speed at the bottom of the inclined plane? This is a little bit tricky as far as English goes, so I'm going to write it out mathematically. Is our velocity at the point where we're half the height of the inclined plane going to be greater than, less than, or equal to 1/2 of our velocity at the bottom of the inclined plane when we traveled the entire height? Um, so if I plug this into our velocity equation that we have here, I'll get our velocity when our height, our distance that we've traveled so far, our change in height, is half the height of the inclined plane. Would be, this is h over 2 times 2g in the inside, gives us gh on the inside of that square root, or root gh. On the other side, I have half of our velocity at the bottom of the inclined plane. So if I plug in h as the total change in h that we have traveled so far, then I'll get root 2gh. If I multiply by 1/2, that'll be root 2gh divided by 2. This is a little bit hard to compare right now, so what I'm going to do is I'm going to pull my constants out and see what happens for my comparisons. If I do that, this is root 2 over 2 times the square root of gh, which is what I had here. Since the square root of 2 over 2 is a unit circle value, I know that the square root of 2 is less than 1. And if I multiply a number that is less than 1 times the same constant, root gh, then I should end up with a smaller value. So this right side is smaller than the left side. Or I could say the velocity at half of the height of the inclined plane should be greater than half the velocity of at the bottom of the inclined plane. Since they asked us to justify our answer, I need to write this in a complete sentence. So I could say The velocity halfway down the ramp is greater than half the velocity at the bottom because our velocity is proportional to the square root of our change in height. Any questions on A part 2?
It's fine.
Part B, I want to derive an expression for the maximum compression of the spring. So I'm going to set our gravitational potential energy equal to our elastic potential energy of the spring. Our gravitational potential energy is still mgh, but our elastic potential energy is half of kx squared, where x is our displacement from equilibrium. My goal is to solve for the maximum compression. Compression is a measure of the displacement from equilibrium, which is x. So I'm just going to take this equation and solve for x. So I'm going to multiply by 2, divide by k, and then take the square root to get my displacement is equal to the square root of 2 mgh over k. Any questions on 2b?
No question.
Okay, 2c. I want to determine an expression for the time that the block collides with the spring to when the spring has reached its maximum compression. So I do have an equation that involves time, which is my period. That's the time it takes to complete one entire oscillation of the spring, is equal to 2 pi times the square root of m over k. The time that we want, the time from when the block collides with the spring to when we reach the maximum compression, would be 1/4 a quarter of that period. So I can just multiply 1/4 times our expression for the period of the spring to get our final answer. So the time that we want is pi over 2 times root m over k, which would be the time that passes from when we collide with the spring to when the spring reached its maximum amount of compression. Any questions on 2c?
No question.
2d. I want to write but do not solve a differential equation for the speed of the block on the horizontal surface as a function of time t before it reaches the spring, expressing the answer in terms of the mass of the block, the height of the inclined plane, the spring constant k, another new constant beta, which is a constant multiplied by v squared to get a resistive force. It doesn't necessarily say friction. But a resistive force, which exists now between the bottom of the inclined plane and the start of the spring. So now, instead of there being no acceleration, which means our velocity would be constant from the base of the inclined plane to the spring, our velocity is no longer constant because we have a force that would give us some acceleration pulling the block to the left, so opposing the motion. So beta is the constant times velocity squared, which gives us the force of that that is pushing the block to the left between the base of the inclined plane and the spring, and any physical constants. So I could say, using Newton's laws, our net force should be equal to the mass times acceleration, but we were also told that the magnitude of the resistive force from the base of the inclined plane to the spring is equal to beta times velocity squared. Since that magnitude of acceleration is going to be opposing the velocity of the block, I could say this force is in opposition to our velocity, our motion of the block. Our block is moving in this direction, which I'm going to call positive from now on. But our force is pushing against the block. In the negative direction. So this is force F is pushing in opposition to the mass's motion after it hits the bottom of the inclined plane. So what that means is I can set ma equal to negative beta velocity squared to get an equation that we can use to set up our differential equation and solve for our velocity. Since our acceleration is the derivative of velocity in terms of time, our instantaneous slope of velocity, that gives us a differential in our equation to make our differential equation that we'll be able to use to solve for d2. Any questions on our setup for the differential equation?
It's okay.
Okay, then part 2. I'm going to use this differential equation to prove that the speed of the block can be written in this form. Okay, this is a pretty unusual form, not a form I would have chosen to use myself. which means we're going to have to solve our differential equation and then rewrite our solution to match that form. So the first step in solving any differential equation is to separate our variables. And this is the most important step in the calculus A, B, and BC exams, because if you do not separate your variables, you lose all credit for the rest of the problem, even if you have steps right after that. So to separate my variables, I'm going to throw all of my t's to one side. So here I have got a dt. I'm going to multiply both sides by dt and move that to the left. And move all of my velocities, my only other variable here, to the opposite side. So that gives me dv over v squared on the right side times my mass is a constant is equal to negative beta is a constant times dt, my change in time. Any questions on the first step?
No.
So on the AP Calculus exam, you will lose 6 points if you don't do that first step out of 9 for one of your free response questions. Because the AP Calculus exam this year for AB and BC is only 2 free response questions. That means once, no, 2/6, 1/3 of your entire test would be lost in terms of points if you did not separate your variables. So, it weighs more than anything else. Okay, so I'm going to integrate both sides. So if I integrate this left side in terms of time, and integrate the right side in terms of our velocity, the weird thing that happens here is our bounds. So my time as the block changes from the base of the incline to the spring would be the time that we had initially to the time that we finish at. So t equals 0 to t equals t, I could say. Our velocity, though, will change from some initial velocity, v sub 0, to some velocity we have at the end of our function, vt. So I'm going to integrate these using those bounds. If I integrate dt, I get t, and then I'll plug in my upper bound and subtract my lower bound. If I integrate v to the negative 2 power, I would add 1 to the power and divide by the new power to get v to the negative 1 over negative 1, which is negative 1 over v. And then I can plug in my upper bound and subtract my lower bound. For the left side, I'm going to plug in my upper bound, so plug in t. This is negative bt, minus, if I plug in my lower bound, 0, is 0. So that's negative bt minus 0 is negative bt. On the right side, I'm going to plug in vt, so this is negative m over vt, minus my lower bound, so that's minus negative m over v naught. Since I'm subtracting a negative, I'm really adding a positive. So that's plus m over v naught. Any questions on my integration, my calculus?
No question for the integration.
Okay, check me on my algebra. I've got, I need to be able to match this form. So what I'm going to do is, it looks like I don't have any m's over the vt's or v naught, so I'm going to divide both sides by m. If I do, this m will cancel. I'll be left with 1's. And on this side, I'll divide by m. So that leaves me with negative bt over m on the left side. And then on the right side, I've got 1's on tops. Then I need to set 1 over vt on its own on one side of this equation. So I'm going to add 1 over vt to both sides, which will cancel this term. Add 1 over vt to both sides, 1 over vt. And I'm going to add bt over m to both sides, which will cancel this term. bt over m to both sides, which gives me 1 over vt is equal to 1 over v naught plus beta t over m, which is what I was looking for. So now I'm in the right form, and we've proven that our equations match using the differential equation that we created in part D. Any questions on what we did?
No question for that.
Okay, now we get to the hardest part. Which I'm going to do from the top, I think. So let me get rid of my picture for the next one. And we'll start over, because I didn't like the way I explained this the first time. So the question was, which I've just erased, for part E, graph x, v, and a in terms of time.
Mm.
Um, for x equals the displacement, from the base of the incline, horizontally, as the block moves towards the spring. If F equals beta V squared is a resistance force opposing the block's motion. So I have three graphs we need to graph. Our position x, our velocity v, and our acceleration a in terms of time. So I'm going to graph all three of those up here, I think. I don't have to be perfect, but we will at least get the slope, concavity, and whether the y values are positive or negative correct, hopefully. Okay, so taking a look at this, what's happening is we have our block that is moving down the incline. Once we get to the base, once we get to the base of the incline, I will have a force that is opposing the motion of the block. Because that force is a mass times an acceleration, and my acceleration is opposing us, our acceleration will be negative, our net acceleration will be negative, which means this position function should be concave down. A is negative, so concave down. A is negative, so y value must be negative. A is negative, so slope is negative. Okay, A is the slope of v, so I know the slope of this velocity graph will be negative. I'll generally be going down. A is the y value of this acceleration graph, so my y value must always be negative. My entire graph that I draw on this side should be below 0 for my y value. And then A is the concavity, the second derivative of my position. So that tells me that my curvature will be downwards for the first graph. Okay, then I'll look at what's happening to our velocity next, I guess. My velocity is decreasing. Um, it's actually the same thing I just did for acceleration. If velocity is decreasing, I need to look for the y value of our velocity. My velocity is positive because our block is still moving towards the right, which is what I said as my positive axis last time. So if v is positive, So I'm not looking for change in v, which is a, which is negative, but I'm looking for the actual value of v now, which is positive, and I know that because the directions of the block's motion has to be positive if we're going to move towards the spring.
Okay.
So if v is positive, that means the slope of x is greater than 0. So my graph should be moving upward. V is greater than 0, so y values are positive for the middle graph. And that wouldn't normally tell us anything about AT. However, we know that f is equal to b times v squared. And if f equals ma, then a is equal to b over m, which is some constant, times v squared, which means my acceleration is actually increasing if our velocity changes. Now, because my acceleration, though, is opposing my motion of velocity, as my velocity gets lower because of the force that's pushing against it, the resistive force, my acceleration will also get closer to 0. As v approaches 0, a approaches 0. Last part, position, which will only affect this graph. My position is always positive. Okay, so ready to graph, and hopefully we will graph in such a way that all of these conditions are true. So walking through them one more time, my x is positive, so that tells me my y value is positive. So I have to graph in this region. My velocity is positive, which means my slope will be positive. I should be going up as I graph. And my acceleration is negative, which means I am concave down. So my graph will look something like this. Starting at 0 at the base of the incline and moving further away. So my x is getting bigger as the block moves to the right. The distance from the block to the incline is increasing, which is okay. X is positive. My v is positive. My velocity is still positive, so that means velocity is the derivative of my displacement. My slope is positive. And my acceleration is negative, so I'm concave down. Any questions on the first graph for position?
Okay, no questions.
Second graph for velocity. For my velocity, my y value will always be positive because our block is moving to the right. But my acceleration is negative, so my slope is negative. I'm going down. So with those two pieces of information, I know my y value is positive. I should be in this region. I started with some positive velocity, so I should start up here. I'm going down, so I should look like this, but I need to know what the concavity is. My concavity is going to be the derivative of a, which, if I derive this, would be 2 times the constant times v to the first power. So my concavity is not 0, which means this will not be linear, and my concavity is positive because my velocity will be positive. So I am concave up. Okay, so putting that all together, my y value is positive because my velocity is positive. My slope is negative because my acceleration is negative. And I'm concave down because my velocity is positive and my derivative of a would be 2b over m times v, which would be positive. So my graph will look something like this. Last part. For my acceleration, we said our acceleration is negative, which means I will have to graph in this quadrant for the first time, in quadrant 4. As v approaches 0, which is what happens as time goes on. My acceleration also approaches 0. And my acceleration starts out being as large as possible because my velocity is as large as possible. So I have as large as possible of a negative acceleration, which approaches 0 as time goes on. Something that looks like this. Any questions on our graphs?
No question.
Okay. I'm sure there's an easier way to do that than just looking at this from a pure calculus perspective like I do, but I don't know it, so I've got to stick to looking at slope and concavity. Okay, so that's it. The homework for physics this time is question 1 and question 3 from the free response questions of the same year, which is 2017. We have only 2017, 2018, and 2019 to go before we are completely out of free response questions. We've done all of the multiple choice questions that I'm allowed to do in person in class before we broke through the online session. So we are completely out of questions as of Tuesday next week. So because of that, I'm going to be moving to AP Classroom, where they've got a couple new questions that they've posted this year that we'll be looking at for the rest of the online courses for the next 2-3 weeks. And then hopefully we'll be back in school and can do some original problems together. All right, thank you very much.